Okay, so let's continue our excursion in the world of 2D CFT, and hopefully we will see some topological line later in this lecture. No, so as a recap, what are we doing now? Well, we are studying 2D CFTs that are unitary, local, and compact. And we are exploiting state operator correspondence and the corresponding unitarity constraints and modular invariance, we haven't used it yet, to constrain the spectrum of operator of the CFT. No? We are doing this because, well, we want to understand what is the symmetry structure of the theory, and in order to do that, we need some information on the spectrum of its operators. And the example that we are using as a example to play with is the Ising CFT. So what we were discussing before the break was now exploiting locality in the form of modularity constraints that arise on the torus partition function of any CFT of the kind that we are studying. And we found that there is a relation between the torus partition function and this trace on the cylinder Hilbert space. And now, because the Hilbert space on the cylinder is a representation of Virasoro, we know that this expression will expand into a sum over Virasoro characters. That's literally just a consequence of the fact that it is a representation. No? So if a theory has a symmetry, then its Hilbert space decomposes into irreducible representations of that symmetry. In the case of 2D CFT, the symmetry in question is Virasoro, and what we get here is just that statement. No? The characters are just defined in this way. And now let's consider what happens using modular invariance. No? Modular invariance is the statement that this partition function has to be invariant with respect to the modular transformations of this torus. No? And the modular transformations are generated by two elementary operations. One is called T, and it acts on tau by shifting it of a unit. You see, like, our torus is obtained from the complex plane by modding out by that lattice, no? So you see, we can shift in the diagonal direction of steps of tau, and we can shift in the horizontal direction by steps of 1, no? So T is just the statement, and then we identify, no? So this quotient means that a point here is identified with a point there, no? So the T transformation is just taking tau, which is a point here, and shifting it by 1, and so going back to the fundamental cell, no? So we expect that there is an invariance with respect to this operation, no? Because it is an invariance of the manifold that we defined, no? And then there is another transformation which is a bit harder to visualize, which is the so-called S transformation, which takes tau into -1 over tau. It is also a symmetry of the torus. No? So invariance under T, if we look at that partition function, what happens? Remember that Q is defined as e to the 2 pi I tau, and Q bar is defined as e to the -2 pi I tau bar. No? So whenever we perform a T transformation, that expression over there that I have put in a box will shift of an amount which is e to the 2 pi I times h minus h bar. Remember that h is the eigenvalue with respect to L0, and h bar is the eigenvalue with respect to L0 bar, okay? So when we perform this transformation, we get a phase like this. And if this thing has to be invariant, then this phase better be 1, no? So from invariance with respect to t, no, we obtain a condition that h bar minus h has to be an integer. Okay, this is a condition which is called also spin quantization. No? This is a consequence of the invariance with respect to t. No? Now, as far as the invariance with respect to S, this is more powerful, but also slightly more tricky to implement. No? And the idea here is that we use the fact that we know how the Virasoro characters transform with respect to the tau transformation. So it is possible, you see, to rewrite them as follows. Here I use a notation, I think it's in the Ginsberg notes. It's I write sum and integral on top of each other. This is very traditional. Because sometimes you will need to do an integral if there are infinitely many spins, if there are infinitely many conformal scaling dimensions. But sometimes you just have to do a sum. In the case of the Ising model, we just have to do a sum. No? And then you get a matrix, which we'll call S, H, H prime. And then we will rewrite it in terms of the characters C, H prime of tau. No? So Virasoro characters have this feature. So and it's very explicit. You can play with them. You can play with them explicitly. And that notation is just there to mean that while for Ising it will be a sum, for more general CFTs it can be also an integral over H prime. No? And now modular invariance, no, is a constraint on this integer n here, no? Because we see that this partition function is expanded in a basis of Virasoro characters. Upon a modular transformation, the Virasoro character will transform with this matrix S, no? And so this expression will stay invariant, provided that S acting on this n here times S transposed is equal to n, no? Okay. Sorry? This integer here, this one is just this integer. No, it's written as a matrix. No, so the idea is that n is a matrix which with indexes h and h bar. No, and we are transforming each of these Virasoro characters with a matrix S. No, so maybe in so S has two indexes. One is h and one is h prime. No. And then there will be an S bar, well, an S for the transformation of this one. These are also Virasoro characters, and they are independent, no? So if I have to write it in, do you want me to write it with the indexes? So it's like S, H, H prime, no? N, H prime, H bar prime. And then we have an S, H prime bar, H bar. And this one has to be equal to NH H bar, no? So each of the these characters will pick an S from this transformation. We are mapping tau into minus 1 over tau, and we want this expression, and tau bar into minus 1 over tau bar, no? And we want this expression to stay invariant, no? This happens only if this equation is satisfied, okay? Now, I want to stress that this is very explicit. So yes. Yes, like when we like it's implicit in the contraction of these indexes, no? Yes. What can I erase? Maybe I can erase this one. I had a question earlier from one of you about whether C and C bar had to be equal or not. They have to be. Because if they are not equal, then we have a modular anomaly. No, there is a problem with respect to this transformation. So we better require this. This is a feature of the Ising model, so it's not a restriction on our calculation. But this is something that we have to assume. It's not something that we'll derive. Yes, exactly. But that was a mistake. Yes. Yes. No, it is. I haven't told you. No, this is a constraint. No, the spin quantization is a constraint. No, so this is a good question. Thank you. Ising, no, for Ising, I said we have H and H bar. They belong in 0, half, and 1 over 16. No. This is consistent with the spin quantization only, so spin quantization implies that H is equal to H bar. This is the only way you can solve for spin quantization with this list of dimensions. No? So this means that the primaries of the Ising model will be one that has labeled 0, 0, one that has labeled a half, and one that has labeled 1 over 16, 1 over 16. This one is the identity operator. This one is called the energy operator, and this is called the spin operator. These are the traditional letters that was carved in stone by Zamolodchikov, I guess. So we don't know yet about the multiplicity of them. So we know that from spin quantization, we know that there are these three, and there are no other options. But we don't know how many copies of such operators there are. No? There might be many. And it is this constraint that will help us, because we know already that n00 is 1, because we assumed that our CFT has a unique vacuum, and by operator state correspondence, the identity is mapped into the vacuum, and so the degeneracy of the identity in the Ising model has to be 1. And so there are only two integers that we need to determine, n half, and n 16, 1 over 16, 1 over 16. No? These are to be determined. And what I was saying is that this computation can be done very explicitly. So we can determine this matrix here, this matrix S, very explicitly. So for a CFT with the same C and with C a half, the Virasoro characters are known and are just as follows. So for H, so C here is a half, and I will just label them by 0. No? So this is the square root of theta 3 of tau plus the square root of theta 4 of tau divided by 2 square root of eta of tau. Higher half of tau is the same, but with a minus sign. And high of 1 over 16 is just, what is it, square root of theta 2 of tau divided by square root of 2 eta of tau. Where these are some famous forms, the Dedekind eta function is q to the 1 over 24. There is a product over n that goes from 1 up to infinity of 1 minus q to the n. And then there is a theta 2. I will just write the sum version of these forms as a reference. And you can look at the Ginsparg notes for more details on how these are determined. This is theta 3 and in C, q to the n squared over 2, and theta 4 of tau. This is a sum over, again, n in the integers. And then we have minus 1 to the n, q to the n squared over 2. No? So just constructing the Virasoro representation can be done explicitly, and one can explicitly construct the Virasoro module starting from the given conformal weights by requiring that it is a highest weight representation, and then one can just plug in the quantum numbers that one obtains into this formula for the Virasoro character, and the result is this one. No? Now, q here is e to the 2 pi I tau. And one can explicitly, by playing with the modular forms in these expressions, implement this transformation, compute chi of minus 1 over tau, and determine explicitly the value of the S transformation here for the Ising model. And I will spare you the sufferance. I will just give you the answer. But I encourage you to try. No? S is a half. And then we have 1, 1 square root of 2. 1, 1 minus square root of 2. Square root of 2 minus square root of 2. And 0. So this is the transformation that we need to plug in here. And we see that the only solution that we can have to this equation, exploiting that S transformation, is that these are all 1. So we have computed the Ising partition function on the torus, and it is just the sum of these 3 characters in absolute value. So the degeneracies here is just 1. And this is isomorphic to the Hilbert space of the Ising CFT on the S1. No? So we have this isomorphism by the state operator map. Now, the Ising CFT is also exactly solvable. So we know, I showed you how to determine the spectrum using unitarity and modular covariance, modular invariance. But the CFT, the Ising CFT is completely solvable. And one can calculate all the correlation functions. In particular, they are determined once we know the correlators of the primaries. No? So we can compute, we can look at the correlators for the primaries inserted on the sphere. And lo and behold, you find out, for instance, if you take a correlator with an odd number of insertions of the sigma field on the field, so odd number of sigma insertion on S2, turns out to be 0. No? Also, if you insert copies of epsilon, it's 0 on S2. So this is the hallmark. When you have some correlators that vanish, no? That's the hallmark for a word identity. There must be some symmetry that protects them, that kills them, sets them to 0. No? So this is an imprint hallmark of a word identity, word Takahashi identity. And in this case, well, we have only a finite number of fields, no? We don't have much room to play with. To a symmetry that can take care of these identities is just a Z2 symmetry acting on sigma. No? So a Z2 symmetry which takes sigma and maps it into minus sigma. No? If you impose this symmetry, whenever you have an odd number of sigma, you find that you pick a minus sign as a word identity, and so this forces these correlators to be 0. No? So this is something that we can take care of very easily. But since this is integrable and is solvable, there are more word identities. In particular, there is a word identity that says that also an odd number of epsilon gives 0. No? And so naively one would say, well, that's another Z2 symmetry and we are done. No? But unfortunately, the correlator of epsilon and sigma sigma, this one, is non-zero. So a Z2 symmetry wouldn't do the job. No? Because if you flip just the sign of epsilon, this would be killed, but it is not there. So this is, indicates that there must be some other symmetry here that explains these vanishings, no? Which is not just a Z2 symmetry, which is not it's a tricky one, no? Because if epsilon were to transform, well, here how can it be non-zero? No, it's very tricky to explain this result exploiting ordinary symmetries. And so the question is, can we explain it using a topological line? So can we explain it? Okay. So to do that, we need to dive a little bit deeper in the structure of CFTs. So what we've done so far was to solve for the spectrum of operators, no? But now we want to enrich the CFT using topological lines. So philosophically, these are exactly the topological line defects that we have seen before. No, so we have our point operators, no, and we have these lines, and we can deform the topological lines in correlators at no energy cost, which is just the statement that if we call the line D, the line commutes with the stress energy. Okay. In particular, we can have an action of the line. Yes. No. Moving things around requires some insertions of the stress energy, and if the line commutes with the stress energy is not going to be affected. So you can move it around at no. Yes. Not necessarily, no. Now we are in general Euclidean spacetimes. No? Of course, eventually we want to insert it on a torus and to play with the lines and modular invariants. No? But and in particular, we have an action of the lines on the operators, no? Defined by this diagram. No? No? So we can say, if I have an operator, a local operator, wrapped by a line, that's equivalent to inserting a different operator, which we call D of O. Okay? Now, since the line commute with the stress tensor, we know that the operator D of O has the same transformation properties of O with respect to the Virasoro. No? So remember that the Virasoro symmetry is essentially just explaining us how we just obtain it from a mode expansion of the stress energy. No? And so the fact that the topological line defect commutes with O, with T, implies that the operator D of O will have the same quantum numbers with respect to the Virasoro symmetry as the operator O we begin with. No? And moreover, these topological lines, we can fuse them, as we said earlier this morning, and they will give rise to an interesting fusion ring. Is part of the definition of the topological defect line, that if you insert it in a correlator and you insert the stress energy, it commutes with it. So they will have a fusion ring, or something like this. If you take two of them and you stack them on top of one another, you obtain a decomposition like this. In general. And notice that this is a relation for the topological lines which replaces the group multiplications. No? So when you work with ordinary groups, the fusion ring is trivial. No? There is no further fusion channel. Here, there are many channels. Okay. So this is the main difference of working with topological lines in general. But since they commute with the stress tensor, they are compatible with our picture. Remember when we consider the Hilbert space of the theory on the circle, if we insert these lines here, no, we obtain a representation of the fusion ring on the Hilbert space. So in particular, we can consider what happens if across the state operator map we have an action of the symmetry on the vacuum. This we can call the quantum dimension. This quantity here, denoted in this way, is the quantum dimension of the topological line. Unitarity implies that the quantum dimension has to be greater than or equal than 1. And if it is 1, then we expect the line to be invertible. And if instead is greater than 1, the line will end up being non-invertible. Something that we will learn how to interpret. For the moment, take it as a definition. Okay, the quantum dimension. Yes? Because the fact that we can insert the topological defect lines on, think about the operator state correspondence, no? Operator state correspondence says that you insert an operator here, you create a state in the cylinder, no? In particular, you can insert nothing, which is the identity, and the identity will give rise to the vacuum here. No. Now, this topological line, no, is topological, and so you can consider if it shrinks and it doesn't wrap anything, it gives rise to the identity transformation. It can shrink to nothing. No? So in particular, we can bubble it out from nothing, no? And we have an identity. So this is equal to this. No? And this is equivalent to inserting it here. But then we can shrink it back to nothing and end up, we must end up with something that is proportional to the vacuum. No? And for this reason, the vacuum must be, must transform like this with respect to the insertion of a topological defect line. The eigenvalue is the quantum dimension of the topological line operator. No? If it is an ordinary symmetry, so an invertible line, you just get 1. Otherwise, you get a tiny rescaling. Now, we can use locality. No? So you see, by locality, if we have a picture like this, we should also have a picture where we insert the line along the time direction. No? we can insert the topological line along the Euclidean time in our cylinder. Remember, no, this is our Euclidean time, and then we have the sigma was the coordinate that was rotating it. So we can extend it along time. If we extend it along time, when we perform the quantization, the radial quantization, we obtain a different Hilbert space. This is called the twisted Hilbert space. So what are if we carry the twisted Hilbert space across the operator state correspondence, what happens? What are the elements here? No? So here we must have a state in this Hilbert space. No? A state in this Hilbert space correspond in radial quantization to having an operator inserted here, but this operator is attached to the line. So we say that this operator, it's an operator in the D-twisted sector. No? So it is like a point-like operator, but it's not really a point because it has this line attached. And the dependence on the position of the line is only topological. No? You can do this construction also if the line is not topological. If you have you can construct a twisted sectors also with non-topological lines, but they won't have a relevance in our context, no? Because we just care about the lines that are topological here. We don't consider defect CFTs. You have a question? Sorry? Yes. Yes. This is our Euclidean time, no? Yeah, like in the state of it's essentially it would be this, no? Like we are inserting D along time, no? And this is essentially changing the type of boundary conditions that we have on the field when we go around it, no? So this is why we get this field in the twisted sector. Yes, yes. It's just that in our time slice, no, in each of the time slices, there will be an insertion of this guy, no? So this in a sense, the Hilbert space, the twisted sector Hilbert space, and the Hilbert space on the circle that we constructed earlier, they are not the same space. They are different. And it is interesting to keep track of them in order to understand what is the symmetry structure of the CFT. I have to stress, I think I forgot, there are references for this part. Maybe I can write it above. So references for this part are two papers. A paper by Bardwaj and Tachikawa. And then a paper of a year after by Chang, Lin, Shao, Wang, and Yin, sorry. Okay. So if you want to learn more about this, you can consult those papers. Now you see immediately that if we have this picture, and that picture of the fusion, the fact that they are compatible gives us a constraint on the coefficients in the fusion ring. So the compatibility with the fusion we'll see that it implies that Nij and k are positive integers. So how do we see that? Well, consider just the twisted sector Hilbert space with the insertion of di tensor dj. You just bring two of them together, no? Bring them together, make them coincide. And then you must have an isomorphism. But now it's an isomorphism of Hilbert spaces. Where here there is a multiplicity which is Nijk times, no? So the fusion coefficients in the fusion ring of our lines must be positive integers because they have an interpretation in terms of the twisted sector Hilbert spaces. Is there a question? They are lines, no? So this is something that extends the notion of an OPE to line operators, if you like. No? The OPE is about bringing point-like operators together. This is essentially the same, no? But now we are bringing lines together. No? So yes. It is related to orbifolds, yes. We will see. So we'll discuss it later, hopefully later today, maybe tomorrow morning. So an orbifold, no, of a CFT is a CFT obtained from the one you start from by gauging a discrete symmetry, no? Gauging a discrete symmetry consists in just projecting everything to the singlet representation, extracting the singlet representation, but then also adding all bound state operators that transform maybe they transform in more complicated representations, no? But they live in twisted sectors. And you have to add them in such a way that eventually the result is gauge invariant, no? We'll be more detailed about it. But of course, yes, you will need you need to keep track of the twisted sector if you want to gauge the symmetry D. But the twisted sector exists anyways. No? It's just that when you gauge, you see, when you gauge D, this line becomes transparent because you have gauged it, so it doesn't act on anything. And you end up with some operator which is just an ordinary operator. No? But in your field theory, when the symmetry acts non-trivially on operators, you have twisted sectors that are related, are just endpoints of the, like endpoints of these topological lines extended at infinity. No, remember that. So this line goes on and on and on forever. No, so that's why we get a different Hilbert space. Now, we want the action of these topological lines to be faithful. Where can I write? Yes, maybe here. No, like we want the action to be faithful. Does it mean that the action is faithful? It means that there is at least an operator on which the topological line acts non-trivially. No? So something like this. No? And if D is not the identity operator, then, and it is simple, which is something that we will say later, this implies that it cannot end topologically. Does it mean that the topological line can end? It means that there are some topological operators that can give a morphism with the trivial line. No? If a simple line can end topologically, then we can take the operator, end the line, open it, move it, and remove it. No? So the fact that the action is faithful means that this is not happening for simple lines. And in general, so this means that these twisted Hilbert spaces, no, when we construct them, they will be non-trivial. No? Because there is always at least an operator which transforms non-trivially, and therefore we will have some elements here. So this might be this might be a good moment for a break. I see that you are dozing off. We resume at 5:05. Sorry? Okay. Okay. So, okay. So in general, no, we can have more defects that come together. No? So in this picture, no, we can have D1, D2, D3, many defects that come together. And that will define for us still twisted Hilbert spaces, no? Which are now related to inserting more lines, no? Along the cylinder. Like this. And by the fusion ring, we still have isomorphism between these spaces and the spaces where the fusion product is occurring, no? And most information about the symmetry category that these topological lines form is inside of these spaces. So if we want to explicitly look and compute about the structure of the symmetry, we need to understand how to control these twisted Hilbert spaces. No? And in particular, I told you, no, that the morphism between lines, no, between lines, they are encoded into topological point operators that we can insert in between them. No? So how do we determine them in this case? No? Well, we have our Hilbert space, twisted Hilbert space for all these guys, no? And so all of them, they meet at a point, no? So it's something like this, say D1, D2, D3, no? Dk, meet at a single point, no? Now, since all the topological lines, they commute with Virasoro, no? These ones will be in Virasoro representations. Because D and T commute, no? So the grading is always given by Virasoro. These twisted Hilbert spaces, they will always occur in Virasoro modules, no? And so they will contain, in particular, a subspace, no? A subspace, we call it D1 dk, no? Which is a vector subspace, which is just the space of those operators, in those twisted operators, that have zero conformal spins, no? If they have zero conformal spins, they are like the identity, no? So it's something that we can insert and it does nothing, no? So they are these junctions. They are these topological junctions, no? So these are the topological points, no? And out of these, we can start computing, and in particular, one of the most interesting junctions to compute is the junctions of 3, no? So these ones, say, will be points in this Hilbert space, no? And it is the structure, computing these ones, allow us to understand what is the structure that generalizes group multiplication, no? You have an ordinary symmetry, no? The spaces are non-trivial only when, if you consider an ordinary symmetry, G1, G2, and G3 here, no? The spaces are non-trivial only if the product of these 3 elements is 1, no? But yes? It's a definition. It's the definition of this subspace, no? Because we are after the topological junctions of the lines, no? In general, you just quantize your theory, you get a Hilbert space of states twisted by all the lines that you start from, no? But if you want to understand what are the morphisms between the lines out of this space of operators, you want to extract the ones that are topological, no? The topological point-like operators twisted by all these defects, no? And they sit in this Hilbert space as a subspace. How do we identify that subspace? By requiring that it has trivial conformal spins, no? These H and H bar are the quantum numbers that say how an operator transforms with respect to the Virasoro symmetry, no? Oh yes, sorry, I meant what they call it, conformal weights. Like we want H and H bar to be 0, no? So that these are topological. We can move them around and they don't cost any energy to do that, no? So this is a definition of this subspace. Yes. So these defects can form junctions, no? When they form a junction, they typically end on a point. This point is an operator in the twisted sector Hilbert space by the operator state correspondence, no? If we are after morphism between the topological lines, we want an operator that is topological as well. It's a point that we can move around at no energy cost. So this is the constraint that defines it, no? The spaces, since the topological lines commute with Virasoro, they are graded by the Virasoro symmetry. the space of topological points or topological junctions is just a subspace of this one identified by this condition. Okay? Okay. So how do we constrain this thing? And also, again, remember, I told you that there is always an inverse, no? So you can always take a D bar, no? Which is the opposite orientation of D, no? And in general, if you consider the space of possible junctions between D bar and D, the dimension here will be greater than or equal than 1, no? And it is simple, the effect is simple, when this dimension is 1. It's a more refined notion. No? So how do we compute it? How do we check? No? So the idea, no, is that remember, when we have these two, there is always a channel which goes to the identity, no? Because we can always take our defect and fold it, no? And we will get a channel that goes into the identity, no? By the folding. So in the fusion of D and D bar, there will always be a number proportional to the identity plus other stuff, no? This one? Yeah, it's the identity. No? Yes. No. But in this case, this one is just a topological point in the Hilbert space of D and D bar. No? It's a point in this, so to define, no? Is just a point where D and D bar meet. No? There is always a topological operator where this happens, no? But there can be more, no? And if there is only one, then we say that the operator is simple. Otherwise, there are more, no? There are more ways D can end on D bar, let's say. Yes. So how do we compute it? How do we determine this dimension? We can consider, again, this picture on AT2. No, consider AT2 partition function with the insertion of these lines. No? No? This one is again related to the so this picture is conformal to the cylinder, and now we are computing the trace, no, of the Hilbert space. But we consider, remember that we have this expression, no? So how did it go? So we have whenever we put the theory on the torus, no, we are computing a trace for the operators here, no? And with insertions of Q of L0 minus C over 24 and Q bar of L0 bar minus C over 24, no? So we're computing the trace of this, but we can consider the limit in which we send tau to I infinity, no? This modular parameter Q is e to the 2 pi I tau. And so you see that if we send tau to I infinity, in this process, we are selecting precisely the topological operators. We are selecting precisely the ones that have h equal to h bar equal to 0. No? Because remember that h and h bar are the eigenvalues for L0 and L0 bar. No? Yes? So do a conformal transformation, no? They are mapped to this, and here, so if you call this operator phi, there is a state phi in the twisted Hilbert space. No? It's the conformal mapping. No? So now we want to compute this dimension. No? And one way of extracting it is to take the limit of tau that goes to I infinity of the partition function on T2 with the insertion of these topological lines along one of the circles. No? And since in the limit of tau that goes to I infinity, you project exactly on the subspace with h equal to h bar equal to 0, you extract from this observable the dimension of this d bar, no? Times, you get q times minus c over 24, and q bar minus c over 24. No? But now, no, you have can use the fusion, and if you use the fusion, then because of this, you have that number times the partition function on the torus plus a sum over k of these topological lines, no? Like this. This would be the stuff that is here. And you see that by the same argument, no? When you take tau that goes to I infinity, this term here is just this coefficient times q to the minus c over 24 and q bar to the minus c over 24. And then here, you receive contributions, but these contributions are in the twisted sector Hilbert space. And for this reason, they always have h plus h bar greater than 0. And so they would just go to 0 in the limit tau goes to I infinity. No? So you see that the dimension of the space of topological points between d and d bar is equal to this coefficient. No? It is the number of ways in which your defect can fuse with its opposite and end up in the identity channel. This addresses his question. No? If your defect is simple, it means that there is only one way in which this can happen. Okay? If the topological line is simple, there is only one way in which this can happen. And this is a way to prove it. And similarly, if you are interested in determining the trivalent junctions, you can perform a similar computation. You can show that if you consider the torus partition function with the insertion of d1, di, say, dj, and dk bar, you can show that the dimension here of v, di, dj, and dk bar is equal to nijk. So just by looking at the twisted sector Hilbert spaces, you can recover the structure of the fusion ring. You can compute it explicitly. Yes? Mm-hmm. But there is a choice, but I think that I mean, there is a whenever you play with unitarity and norms of states, no, and you work with an Euclidean CFT, there are choices, no. In our context, since we have in mind a CFT which is obtained as a weak rotation from a Lorentzian version, then that one uniquely constrains the unitary structure that you are using to compute the norms of all the states. No? I think that if you do that, you will end up with a vacuum state which doesn't have unit norm. No? I think that eventually, if you do that, no, it will affect the normalization of the vacuum. We can process it, yes. Okay. So in this way, you can exploiting the structure of the twisted Hilbert spaces, extract the coefficient in the fusion ring. And remember that we spoke about these F symbols earlier. The F symbols in this context, these associators that we were talking about, can be introduced by thinking at the junction of four objects, 4 lines. No? And you see, like, here you have your Hilbert space, say V, D1, D2, D3, and D4 bar. No? And there are 2 ways of resolving this junction. No? There is one way, like I won't draw the orientations, which goes like this. And here, you see, you have to sum over all the fusion channels. And then there is another way in which we resolve it here. No? So we can resolve it either in this way or in this way. They're always summed over all the fusion channels. And what is an F symbol? An F symbol is a change of basis to describe, so you see, if you work with this or with that resolution, you get different bases for this Hilbert space. An F symbol is just a convention that says how it's a change of basis. So you can consider, take this one, write it like this, summed over B, and you have your F symbol. And this will depend on A and B. No? So in the case of an ordinary symmetry, all these fusion channels are points, and this one is a number. No? But if you have a general topological line, then there are more labels here which are related to the choices that we have here. No? We have elements in these vector spaces. And our F symbol will depend also on all of these data. Okay. The F symbol, you remember when we spoke about the associator morphism in the first part of today's lecture, that one in this context is encoded in this change of basis. And the pentagon identity that we discussed earlier is just related to the fact that if we now consider the Hilbert space of 5 objects, this is 5, by topological moves, we get relations between the F symbols. And now this one goes like this. So you see, here I just used this resolution, this relation between this resolution and that resolution to move this line here. Then I used it on this segment to get here. Then I used it on this segment to get there. And then I used it lastly on this segment to get here. Okay? And you see that there are these 5 elements, 1, 2, 3, 4, and 5. They are the 5 F symbols in the pentagon identity. And it is a deep theorem that if you have a fusion category that has a finite number of simple objects, no? And an F symbol that satisfies this pentagon relation, that's all the data that you need to fully and completely characterize the fusion category. So once we can compute the F symbols, in the case of 2D CFTs, we are done. We don't need any extra data. Okay. Now, there is one last piece of information before we can go on and compute what happens for the Ising CFT. So you see, like, so the moral of the story, if you like, is that the very sketchy picture that we drawn this morning, no, has a very concrete realization in terms of the structure of the twisted Hilbert spaces and the sector of topological operators in the twisted Hilbert spaces in any CFT that satisfies the axioms that we are studying, that we stated at the beginning of the lecture. So unitarity, locality, and compactness. Okay. And it's extremely explicit. You can literally compute it, and we will do it for the Ising model. Before we can analyze that, there is one last piece of data, which is related to the action of the symmetry on the defect Hilbert space. I want to mention. So you see, if you want to act with a topological line on your twisted Hilbert space, so say that you have the Hilbert space twisted by the defect T1. No? Here you have your state. This belongs to this one. No? So remember, in order to act, we just have to insert it horizontally, no? So you see, there will be a topological junction here. No? So when we want to act with our topological lines on the states in the twisted Hilbert space, we just insert it horizontally along space. No? When we want to twist the Hilbert space, we insert it vertically. No? So if we go in the plane, so that state becomes an operator inserted at the origin, which is a twisted operator, so it is attached to a line. And this topological line, just encircle it along the conformal transformation. And we have this vertex here, our topological junction. And now, well, we have seen what to do if we have topological junctions of four lines. We can resolve them, no? So here we can also resolve it. And here you have your D1 that goes on, no? And in the middle here, we have to insert another element in the fusion channel of D1 times D2, no? So if the symmetry is invertible, there is only one fusion channel, and this doesn't do much. If the symmetry is non-invertible, there are more fusion channels, and there are many ways of doing that, which are parameterized by these topological junctions, no? So if you want to understand how your symmetry, your topological symmetry act on the twisted Hilbert space, this is encoded by the F symbols that are capturing this resolution, no? More generally, if you have you can have actions of this type. You have your twisted sector operator, you have your line, you have a junction here, you have the line D2, and this one can fuse into another defect. And an action of this type, so here again you have your topological junctions, no? An action of this type will just induce a map from the twisted Hilbert space by defect D1 into the twisted Hilbert space with defect D3, no? By the defect D3. So these representations of the fusion ring on the twisted Hilbert spaces have a name. These maps, they go under the name of tube algebras in the literature, and they are interesting to study and characterize explicitly, and they can also be used explicitly to give a straightforward way to compute the various F symbols, no? So the formalism developed by people studying tube algebras, because of this interpretation, can be used to compute these different ways and different changes of basis that are associated to the F symbols. Okay. Now, what is the tool that we are going to use to constrain the structure of these twisted Hilbert spaces? It is again the deep interplay with locality and modularity, as we did previously today for the case of the untwisted Hilbert space. So this gives rise to a way of essentially doing a modular bootstrap on the structure of the spectrum, no? So you consider the partition function on a torus, and you consider it with an insertion of D in this direction, but by the S transformation, this is mapped to a partition function on the dual torus with the A and B cycled swapped. Ah, eccolo, yes. Sorry, there was a question before about a way of visualizing the S transformation in in the torus, you can think of it as a transformation that swaps the A and B cycles. Sorry if. So you see, if we consider this picture here, no, this picture here has an interpretation as a trace in the ordinary Hilbert space of an insertion of the topological line times our Virasoro generators, no? So this side has this interpretation. But now by modular invariance, we see that this one is also equal to the trace on the twisted Hilbert space of an insertion of just the same term that arises from the Hamiltonian and the shift on the cylinder, where now Q tilde is just e to the 2 pi I minus 1 over tau, no? But because of the invariance with respect to the action of the S transformation and modularity, we expect that this trace on the twisted Hilbert space with the insertion of the defect of the topological line becomes equivalent to this one. Since the topological lines commutes with the stress energy, we know that this space is also going to be organized in a representation of the Virasoro. And this gives rise to, again, an integrality constraint, as like the one that we've seen earlier today. No? So we have a sum, say, over h and h bars, now of n, h, and h bar, of chi h of q tilde, and chi of h bar of q tilde. These are, again, going to be positive integers. These are, again, going to be Virasoro characters. But now these ones, no, are related to the decomposition in Virasoro modules of the twisted Hilbert space. No? And so on one hand, we have the action of our topological line on the ordinary Hilbert space. On the other hand, we have the multiplicities of the twisted Hilbert space, and the two must be equal by modular invariance. Yes, thank you. This is Q bar. And also here it's Q tilde bar. Yes, thank you. Thank you. Sorry for the typo. Positive integers because they represent the multiplicity of a module of an irreducible representation in the decomposition of this vector space. This is why we have this is a very powerful equation. No? So let's see what happens in the Ising model. You see, like when we act with D here, we will get a decomposition, no, in the eigenvalues of the action of the symmetries on the various operators. No? So if this is the right-hand side, no, of that equation, the left-hand side, you can write it like this. We know that there are only for our Ising example, no, C is a half, and the allowed H's are only 0, a half, and 1 over 16, no? And so on the left-hand side, this action here, we know that we have computed and showed explicitly that there are only 3 possible states: the identity, the energy, no, the associated by the operator state corresponding to the identity, the energy, and sigma, and the spin, no. And so in this decomposition, what do we get? We get an equation. The left-hand side will be something that looks like this. It has an A, no, of D on the identity, times chi0 of tau square, and then plus, say, a of d on epsilon times chi of a half tau squared plus a d on sigma times this character, no? So these are a sigma d, a epsilon d, and these are the eigenvalues for the action of d on this operator, on the identity, on epsilon, and on sigma, by this linking action that we discussed. So we have d, and now we insert our topological line, and now this one has to be equal to this expression. Okay? So you have an equation in these two quantities. These are the eigenvalues for the action of d on the states in the Hilbert space. They describe how your state transform with respect to the action of d. Remember, when we insert d along the spatial circle in the twisted Hilbert space, we get an action of the topological lines on the Hilbert space, no? And so we get a powerful equation here, no? Because we know explicitly what are the possible Virasoro characters, and so we can look at possible solutions of this equation, no? These are transformed, Q tilde transforming here. We know how the characters transform with respect to a modular transformation, no? And it is the S matrix that we wrote earlier today, no? And so we can solve this constraint explicitly. We can look for solutions, and the solution will tell us what are the possible actions of topological lines in the Ising CFT. No? And I invite you to check that solution has only that this equation has only 3 solutions. So there are only 3 solutions. So let's call AD identity, AD epsilon, AD sigma. And so they are 1, 1, 1, 1, 1, minus 1. And then there is another one, very weird, that looks like this. So this transformation is something that leaves everything invariant. So this is the trivial line. This is the identity, no? The transparent line. This transformation here, do you recognize it? It is the Z2. It is the Z2 that acted on sigma. The topological line corresponding to it, it's conventionally denoted, traditionally denoted eta. This guy is weird because it has a kernel. So we call it N, because we don't want to believe in it. No, we call it N, also traditionally. And you see, like, it has a very strange action. It has a kernel. It is a topological line that is non-invertible. It's a kernel. No? From this structure of eigenvalues, we can also read off what is the fusion algebra. No? We can see that if you take n squared, or n tensor n, you get 1 plus eta. Just look at the eigenvalues, no? If you take eta squared, you get 1. And if you throw n against eta or eta against n can absorb the eta line. So this is the fusion ring. And we got it from the modular bootstrap. And Yeah, unfortunately, I don't think I will have time. Unless you want to go a little bit over time. Can we go a little bit over time? Is that okay? Yes. Yeah, like I should be over now, I think. But maybe I go until 6. Is that okay? Yes. Can you? No, it's not. Yeah, okay, okay. No, I'm tired as well. um, yeah, it's better to do it. It's better to do it well than to do it in a rush and then have to get a lot of questions in the Q&A tomorrow. Okay. So let's stop here. We got the fusion ring. We got these coefficients. Please don't erase this blackboard. Okay. And we catch up tomorrow.